Hello, my dear students. Warm welcome to all of you. We are with physics now. Okay, we'll be talking very seriously about physics now. Okay, myself is Dr. Shobboshachi Shen. I'll be offering you the physics courses, course objective, course outcome. You can see on the screen, and we are in outcome-based education. So every course is mapped with what is its probable outcomes, which I have illustrated later on. Now there are five modules. Now we'll be adapting one by one to each module and explore the world of physics. Now let us explore what is the topic of the day. You should keep one thing in mind, that whatever we teach in these classes, each video lecture is basically a building block of your future engineering courses. Each class is going to give you some fundamentals, some new concept. And if you add all those concepts at the end of the semester, you will get the correct path of entering into your own engineering curriculum, because all your curriculum are essentially the application of physics. Engineering means physics applications. So let us explore it a bit more. Hello, my dear students. Welcome to my last class on the course of Physics 1. And I'm very thankful to all of you for this long journey. We have started with very small microscopic world of quantum mechanics, and now actually I'm moving towards the most modern topics, the most modern optics. We studied called lasers, and after that we had made our life a bit classical. We talked about few classical topics, few classical ideas. One of them obviously and of course includes the concepts of those waves and oscillations. And now we are in the optics, physical optics. We cover topics of interference, we cover topics of single slit diffraction, double slit diffraction, and now from the last class onwards, we are now covering the multiple slit diffraction, which in a better language is called grating. And you have actually noticed that in a single slit diffraction, how the diffraction pattern looks like. And also you have noticed that when you get into double slit diffraction, you get an additional interference term. And now there are two slits. Now when you get into many slits diffraction, you get an interference per term to n number of slits. So all these things was discussed last week. So today's the objective of today's class is to talk about some more aspects about the intensity distribution spectrum that you see with the grating. We will highlight about an interesting idea called resolving power of a grating. That is how well it can resolve the spectra of two different colors, very close dispaced colors of light, and also the few pertinent issues like absent spectra or missing order in the diffraction grating. And another wonderful idea, obviously, to apply this whatever I taught related to the grating in some problems. So we'll solve some problems today. So now let us concentrate. This is me. You can anytime, anywhere, available in these numbers. And this is obviously, I have been telling you every day, we are focusing on electromagnetic waves. Okay. So very important term is this concept of path difference and phase difference. You multiply the path difference with 2 pi by lambda, you get the phase difference. Diffraction means departure from rectilinear property of light. I so often told you
The classical theory tells us light wave will not go to the other side if there is an obstacle, but diffraction tells us it can go. Diffraction can be of two types. Front of a glass, this is front of a glass where source and screen, both of them are at infinity. Okay, you are assuring that to lens system and Fresnel glass, the source and screen will be at finite distance with respect to the obstacle or aperture. This is a clear example of single slit diffraction. And obviously, we made a thorough discussion, thorough analysis of what happens with one slit. Initially, we calculated the intensity at a given point. At the point OPRI, according to the description, it will result in a central maxima, but diffracted beams are reaching the point P, so it was calculated as dz. After that, contribution of all points, according to Huygens principle, all points in that single slit are acting as a secondary wave source, so their contribution was added. So they are reaching the point P differently. As a result of that, a phase difference was there, and ultimately this phase difference was calculated following this formula. And obviously, if you calculate the phase difference, and you can write down this expression in this way. And after that, actually, we considered the entire range from minus d by 2 to plus d by 2. It was integrated. So this was a contribution of one slit. We had a lot of discussion. This is a called single slit diffraction pattern. Okay, what you see with the diffraction pattern with one slit. Okay, the central maxima, minimas are there, secondary maximas are there, all these things are there. Now, the moment you go from one slit to many slits, this single slit diffraction pattern actually gets enveloped inside some interference intensity distribution. Okay, so this was a case of two slits, double slit that I also discussed in your class. Only difference was that now both the slits are contributing. The waves that is being diffracted, they are now superposing at the point P. So basically an interference term would be there because of the two sources, okay, two slits. So that will be there. So after that, we made this calculation from single slit to double slit. Only change that was taking place actually because of two slits, I have added the contribution of both the slits. So if the separation between the slit is like D, the grating element, sorry, in case of slit, two slits, there is a question of grating actually D is equal to A plus B, okay? A is the width of the aperture and B is the width of the opaque space, and geometry suggests, okay, you can see D is equal to A plus B. So it will be integrated from for the first slit minus A by 2 plus A by 2 for the second slit, D will be added. So ultimately you get a term which is a contribution of both this is the contribution of both the slits. So our next job was to integrate those two sinusoidal functions, okay? We did it, we made a lot of calculations related to double slit diffraction pattern, and we got this type of pattern. Okay, the envelope is that of the interference, so dotted line, and inside that you can see the single slit diffraction. Okay, so realistic pictures are like that. Okay, where you can see the intensity distribution. Missing orders are also there. The idea is that if the two things are coincident, principal maximum one of the say the diffraction pattern interference distribution coincide that of the minima of the single slit one, then the orders will be missing. Now after that we will study in the previous lecture into multiple slit diffraction. So these are many slits are there, all slits are of equal width, all slits are of the equal opaque space. So grating element, this is called the grating. Okay, many slits are there. Large number of parallel slits will be making a grating. Diffraction grating can have two classes. One of the grating is called transmission grating, and the other one is getting called the reflection grating. We mainly focused on transmission grating, how it is created, all these to be also mentioned, and lastly also how we actually reflection grating that I also mentioned. This is the way grating is produced. So that idea also I shared with you. Okay, and this is called replica method of production of grating. Today our objective is slightly different. Okay. You can see there, this is a grating that we use in the physics laboratory. Okay, and you can see, look at the right hand side picture, the animation is on there. To see the picture, you realize, okay, these are multiple slits. You see, this is what you see. The left-hand side one is basically a student's rating. Now, another important issue is obviously to calculate the intensity due to many slits. So this is the picture that will decipher everything. So this lens system at O prime, you get the central maxima. Now diffracted beam is coming at the meeting at the point P, according to my description. All the beams are actually diffracted by some angle. So they will be called, because they are reaching at the point P differently. So basically they will be making a phase path difference between the waves meeting at the point P. Path difference will lead to phase difference and also the change in intensity of the superposing waves. So that change in intensity calculated, I reminded you what happens with one slit. Just now I told you. Okay. After that we get into the single slit to slits and two slits. So now we are moving into many slits. Okay. Many slits. Okay. This is the two slit. The two terms are there. Okay. They are coming from slit 1 and slit 2. Just imagine you have got so many slits, split 1, split 2, split 3, and split n. So on. In between many other splits are there. So final displacement will be in summation of the contribution from all the splits. Okay. So this term, okay, it is being contributed by all the splits. This will be contributed by one split number 1. This will be contributed by the split number 2. The third term is contributed by split term 3. So they are additive, okay, to produce the final intensity. Okay, and similarly up to nth sum we get to n, and many of more points will be there. This is for the nth. So basically, your job is to get the intensity means to add all those points, okay, all those contributions from the individual states. If you could do so, then you are done. Okay, so it's the nth. So now, if I move forward a bit, you can see here, same story. This a by 2s are again defined. So basically, the first term, if it is from 1 minus a by 2 to plus a by 2, the second split will give you d minus a by 2 to d plus a by 2. Third split will give you 2d minus a by 2 to d plus a by 2, and so on. And nth split will give you n minus 1 a by 2 to n plus n minus 1 a plus n plus 1 a by 2 plus d. I'm sorry, n minus 1 d minus a by 2 to n minus 1 d plus a by 2. And you get a summation like this. Okay, it's a long term. Everybody will contribute. Everyone is contributing. If you go to the next page, you can give better picture. You can see first term minus a by 2 to plus a by 2 from the split 1, and if you add d, move into the split 2, so d minus a by 3 plus a by 2. Integration is very similar the way I did earlier. Next one is 2d minus a by 2 to d plus a by 2, 3d minus a by 2 plus a by 2, and so on. For the nth one, n minus 1 d minus a by 2, n minus 1 d plus a by 2. So your job is to add all these things to get the total intensity distribution that I discussed. So now today I'll move forward a bit. I'll talk about two important issues. Okay, this is a pattern that you can see here: missing order and resolving power of it. So to do so, let us keep three things in mind. What is the final intensity? Okay, the final intensity expression you should always remember. The In case of a grating, the intensity is equal to I0 I0 is corresponds to the maximum. The single slit pump sine square in beta. What is sine square? Alpha equal to IA sine lambda. Beta is equal to d sine theta by lambda. So you know, this is your rating. This is A, this is B, and A plus B is D, the rating element. So from this expression of intensity, I actually told you about the attainment of, or from here on actually utilize this expression. If say I is equal to I0, so first is the condition of central maximum. That is for alpha 0, beta 0. And alpha 0, beta 0 means, you know, obviously, pi a sine theta by lambda, and this is going to pi d sine theta by lambda. This is also going to, so that means this angle of diffraction is going towards 0. Now another issue that I discussed also, just add one more page from the pen. That is this intensity maximum maximum. That is beta. This is one of the condition of getting the maximum. And another interesting observation, because the condition of maximum, there are a few conditions of minimum also. So beta equal to, so from here on, we can actually now write down that beta is therefore pi and pi cancel. The condition is this. This for the nth order, I will call it n lambda. It's called the equation of the grating. This equation, d sine theta n, the condition of getting maxima d is a plus b, is getting equation. Condition of the maxima of the getting part. This is the maximum of the getting. Okay. So what would be the order of the principal maxima? The 0th order is obviously the central maxima, and the others are equal to 1, 2, 3, etc. Apart from the principal maxima, there will be two secondary maxima and secondary minima also. Now, secondary minima is coming for the numerator of this expression. See if I show it here. If I show it here, so therefore, secondary minimum is I achieved it yesterday. I is equal to I0. For secondary minimum, this will go to 0. So sine n beta 0 means pi beta plus p. From here on, I can write down n pi d sine theta by lambda equal to plus minus p pi. This gives me this much. Pi will cancel. This gives me obviously d sin theta is equal to s minus p by n lambda. This is the condition of secondary minimum. Okay. And obviously p value should be 1, 2, 3. P other than n, 2, and 3. Okay. Because actually using the first order maximum. The principal maximum. Now secondary maxima can be obtained. So this is the secondary minimum. You can see there will be n minus 1 such minimum will be there. Now if I look at the secondary maxima will be obtained. So let me show you again. I is equal to for secondary maxima. It is derivative di dv. It should be 0 for the optimum value. If I do the necessary mathematics, okay, then it will be like this much. N tan beta equal to tan of n beta. And this is the value condition of secondary maxima. Now beta will be other than plus minus n pi reducing secondary principal maxima. Basically, you can also find out many more interesting things. Beta is other than plus minus n pi. Which is resulted in the first order maxima. It's not central maxima. So basically, these are the my keys to progress. Now we're talking about a very important issue. It's called absent spectra. The spectra will be absent if the principal maxima of a particular spectra converges from the interference spectra. If it converges with the single state diffraction minimum. So absent spectra is spectrally absent if principal maxima that is mainly coming from interference term coincides with single state diffraction minimum. That means I have to take up both condition. Now, what is the condition of the principal maxima? Regarding equation a plus b sine theta n. And what is the condition of the single slit minimum? A sine theta n equal to n lambda. So this is a condition for minima in the diffraction, and this is a condition for maximum. This is maximum. They coincide. These two has to coincide. If they coincide, then I'll get a absence spectrum. Okay. So basically, I'll be taking up both the equation. I will not take a ratio of both of them. If I take a ratio of both of them, so you can see A plus B sine theta n is from maxima, and A sine theta m, this is for minimum. This is the interference maxima or multiple slit. This is coming from the diffraction pattern in many slits, and this is from single slits. So I take a ratio of them, A plus B by A, in the nth order. For the nth order, is basically sin theta will be cancelling n by m. So this is the condition for the absence spectrum. Now let us vary which one, how is spectrum absent. You can always analyze that easily. You can always analyze that. A plus B by A equal to n by m. Now let us take a few cases. Suppose the B is equal to A, that is opaque space with and the slit with the same. So then this equation becomes n by m is equal to 2 by 1, n equal to m. So for if you vary m as 1, 2, 3, so corresponding n would be like that. The second order, fourth order, and the sixth order maxima, these diffraction maxima would be absent. These are called missing orders. Now let us consider another. When you consider this equation, A plus B so if I consider B is equal to A, That means if this is a grating, if this is A, this is 2A. Okay, this is double. So this is your grating. Then how many orders will be missing? We can predict here. This is 3 by 1 n by m. So n will be equal to 3m. If you vary m, 1, 2, 3, etc., then the order will be equal to 3, 6, 9, 12. So these orders will be missing. So these are the missing orders. They will be absent in the final spectra. Okay, or missing order for this particular case. We can see it is depends on the way you are choosing the grating, you are preferring the grating. Okay, so it depends on that way. Another thing you can always do, suppose there is no width at all, that converts to the case of no width at all means this case, no width at all. If you do that, then this case will become suppose B is 0, no opaque space. If you follow this formula, n by m equal to 1. N by m equal to 1 means all those this interference terms is missing because it is now converging to a single state diffraction because there is no opaque space in between. Now another wonderful idea that I'm sharing here now, the dispersive power of a grating. We studied about dispersive power of a prism, that its ability to disperse the electromagnetic radiation. Now dispersive power of a grating is basically if the diffracting angle of diffraction is theta, then incremental change in the angle of theta. And because of the variation of wavelength is d lambda, d theta d lambda is basically the dispersive power of the grating. So if you now look at the equation of the central maxima, if you look at the expression of the central maxima, this gives me a plus b sine theta n lambda. So if you take a derivative of this, d of this, then this is a plus b. If I take differential, a plus b cos theta d theta n d lambda. So this obviously gives you d theta d lambda equal to n by a plus b cos theta. This is your expression of the resolving power of everything. Okay. Sorry, resolving power. Dispersive power of that. This becomes the expression of the dispersive power. So this is the dispersive power of the. So if this is dispersive power of the grating, obviously, if I write down separately, in a more interesting and analytical way, you can write as d theta d lambda is therefore n by a plus b cos theta. So this dispersive power of the grating, it depends on n, the order number. It is inversely depends on 1 by a plus b, which is nothing but the number of rulings. And also, it is inversely depends on the cosine of the angle of diffraction. Okay, it also depends on the inversely on the cosine of the angle of diffraction. Okay, so therefore, with this in mind, let us again introduce another wonderful idea, that is the concept of resolving power of a grating. Now, in a grating spectrum, okay, the concept of resolving power is that it's the ability of the grating to produce or to distinguish between the spectral lines between two nearby wavelengths. So let us introduce the concept of resolving power grating. Resolving power is basically, it is the ability of a grating to distinguish between the two spectral lines of nearby wavelengths. Suppose one of the wavelength is lambda and the other wavelength is lambda plus d lambda. So then the resolving power is defined in this way. Then we define resolving power in this way. It is defined as like this way. Change the color. So resolving power from here on, RT is basically defined in the wavelength by change in wavelength. It's called the resolving power. The standard definition of resolving power is now calculated. Now let us see. So you have to see how it changes. When we'll say the two spectra are resolved, two spectral lines are wavelength lambda and another I'm using lambda plus d lambda. Okay, now they are just resolved. We'll say they are just resolved if suppose these are the two spectral lines. I can say them just resolved if the minimum of one of the spectral line is a minimum. So this is a maxima corresponding to the wavelength lambda. It is a minimum corresponding to the wavelength lambda. If it converges, okay, with the maxima of the wavelength corresponding to lambda plus d lambda. Okay. Then there are, because then and only then I'll make a central maximum of one pattern. This is a central maximum of this one. It is coinciding with the minimum, first minimum of the second one. Okay. So obviously the related condition will like this much. The condition of the central maxima of the lambda plus lambda plus d lambda is what? A plus b sin theta lambda plus minus d lambda. This is central maxima. Now this is going to converge with the second, make it the minimum, first order minimum is this one. This is basically b sin theta a plus b. And the minimum. So this is a condition of the minimum. Now this will convert. Okay. If I make an expand, lambda its maximus condition is a plus b sin theta. And the minimum condition is n lambda. So obviously I can consider both the equation and write down. So n lambda will cancel from this equation. This is the expression of it depends on if it's proportional to the number of reads. So more reads wins, better resulting part. That's the honor. I will solve one to problem now. Obviously, past problems. So I've got several beam of light coming. My problem. Some of them using a parallel beam of light. Then and it is called normal. Your job is to find out the angle of diffraction. Or first, all of us know this is my getting equation. So let's solve the equation. Answer of the problem would be like this one. Our condition of the central maximum. Now here, some of the information are given. There is number of rulings is given by 42500. I missed it. It's nothing but 1 pi plus b. So obviously, you can now slightly manipulate this equation. Here is 1 lambda, it will be 1 by a plus b and prime lambda. So automatically, sine theta in prime will be 4250 and lambda is in 5890 centimeters to the power minus 6 centimeters. So if you put all these values, from here on you can calculate theta as 14.5. So this is one. Now I'll solve another problem. This problem is actually related to the concept of number of links calculation, etc. Suppose we consider diffraction rating of the types of the diffraction between A is equal to 0.1 centimeter, B is equal to 0.2 centimeter. The wavelength of the radiation is 5.5 10 to the power minus 5 centimeter. Question is that what is getting another? which you can easily calculate just by adding it plus b. And number of lines or number of units are simply that. To answer this question, obviously, I consider the b is equal to a plus b. So if we adding this point equal to the 3 it is given there. And also you know the written equation is t sin theta and lambda. So the maximum angle is possible. The maximum order number possible is basically for 90 degrees is 0.002 m and lambda. So this gives you this much. Maximum order that is possible is point lambda is 5.5 minus 5. So if you put the values, this will be like 5. So maximum of the 5 order can be seen. And the number of lines is the same. We are taking it into one binary space. If you do distribution, then do it also is like 3 by 1 by something. So last problem is this series will result in power. Okay. That's the nice. What is the problem from? What is the minimum number of lines in a greeting? Into resolve the third order spectra formed by the greeting of lines having a length lambda is equal to 5890 angstrom. To solve this question, Resolving power is lambda 1. Lambda 1 is 3. Number units. The order is 3. So lambda is 5.90 and 6. This gives me the value of 2. It's 300 something. So value of n is 7. So this is the number of units. Okay. So this is minimum limit. So I tried to solve a number and variety of problems in so this in mind, I get back to the so we talked about DC order, the resolving problem. So thanks for staying with me for such a long time. Bye bye. This is
You and me were meant to be in the great outdoors, forever free. You and me meant to be in the great outdoors, forever free. Like a bird on a tree, I'm just sitting here. I got time, it's clear to see. From up here, the world seems small. We can sit together. It's so beautiful, you and me. We meant to be in the great outdoors, forever free. Sometimes you need to go and take a step back to see the truth around you. From a distance you can tell. You and me were meant to be